All right, so for simple harmonic motion, that's any kind of motion that moves back and forth that's caused by a force, and that force has to be directly proportional to its displacement. So for example, if you look in this picture, right here in the middle, this is when something is in equilibrium. If I stretch the spring, like I am in the top picture, that would give me a displacement of x. This right here, this displacement would be x, because I'm pulling it this distance and it's stretching. If I were to compress the spring, so that would be the bottom picture, I would also move a displacement x if I apply the same force in the opposite direction. So basically, it will zigzag back and forth. So if I stretch it, it will then stretch one way, return back to equilibrium, stretch the other way, return back to equilibrium over and over again. And that's what simple harmonic motion is. So that's our first slide. If I scroll down, based on this idea of simple harmonic motion, that things bounce back and forth when you stretch or compress them, this guy named Robert Hooke realized that as you stretch springs, that as you add more and more force, the spring will stretch a proportional amount. So if I pull twice as hard, the spring should move twice as far. And Robert Hooke is the one who figured that out. Now his law, when he determined it, he found out that there was a constant of proportionality, or a spring constant. Now this right here is a lowercase k, and we have to use lowercase k because capital K is already taken by our kinetic energy formula. So we calculate the force from Hooke's law, the force on a spring, as the spring constant k, so we've got our spring constant, times our displacement, x. And this right here would be our spring force. And if we do some rearranging to solve for k, k would equal our spring force divided by x, and we measure forces in newtons, and we measure displacement in meters, which is why our unit for our spring constant is the Newton per meter. Now this negative sign that appears right here, this negative sign, is because the spring will always try to return to where it was. It's called a restoring force. So if I pull something to the right, if I pull a spring to the right, the spring's going to try to snap back to the left in the opposite direction that I'm pulling. So that is why it is called a restoring force. Now we usually will use Hooke's law to figure out something about an object using a spring. So for example, if you have an object hanging from a spring, then the weight of that object will equal the spring force pulling up on that object. So this is an object hanging on a spring. You could find what the mass or spring constant is of that object if you know like the weight of it and then the spring force that it's pulling with. We can also use F equals ma if something's launched from a spring, and we will look at that on our next slide. So if we start here with our equation, so a load of 50 newtons is attached to a spring hanging vertically, and it stretches the spring 5 centimeters. The spring is now placed horizontally on a table and stretched 11 centimeters. And we're going to figure out what force is required to stretch the spring this amount. So the first thing I'm going to do is I'm going to draw a free body diagram. So I've got my box. You can draw a spring like little squiggles. So I have my spring force upward. And I have my pull force downward from gravity. So this is caused by the spring. So F with the little s is the spring force. The force of gravity is from the earth. So I've got what's causing those forces in parentheses. Now, because it's hanging, this right here is what tells me that it's at rest. It's not moving. So the sum of my forces in the vertical direction will be 0. This means that the spring force plus a negative force of gravity, because they're pointing in opposite directions, has to equal 0, which means that these forces are equal in magnitude but opposite in direction. So if I set this up, my spring force is the spring constant times the displacement, and that's going to equal the weight, mass times 9.8. So to keep things simple, I'm going to use 10 for the acceleration due to gravity, and I'm going to use this to solve for k. So k times my displacement, which is 5 centimeters, and remember 5 centimeters is going to convert to 0.05 meters, is going to equal my mass times my acceleration due to gravity, and this right here is my weight, my Fg, so that is 50. Now if I do my algebra, 50 divided by 0.05, if I zoom up here, K will equal 1,000 newtons per meter. So I had to look at the vertical component of what's going on in this problem to figure out what my spring constant is. Now that I know my spring constant, I can move on to part 2 of this question, which is to figure out what force is required to stretch the spring this amount, and I'm stretching it 11 centimeters. So now I want to know how much force, if like this spring's attached to a wall, how hard I have to pull so that my displacement here is 11 centimeters, which equals 0.11 meters. Now since I'm moving horizontally and I'm stretching it, it's not going to move, so I'm going to have the sum of my forces in the x direction equals 0. I have an applied force to the right, and my spring force is going to oppose me to the left, because if I let go, the spring is going to want to zoom back to its equilibrium position that it started at before I stretched it. So I have my applied force plus a negative spring force, and again, I'm just using left and right to decide my positives and negatives. This means my applied force is equal to my spring force. So I want to know how much I'm pulling, and to do that, I'm going to use the fact that my spring force is found by doing the spring constant times the displacement. So I'm going to use the spring constant I found in the previous part of this problem. So I've got 1,000. I'm going to times that by 11 centimeters, which is 0.11 meters. And when I do my multiplication, I get an applied force of 110 newtons. So if I wanted to determine how hard I'd have to pull, I would have to pull with 110 newtons to stretch this spring 11 centimeters. So that is an example of how we're going to use Hooke's law to calculate things in the horizontal and vertical directions when we have different problems. Now, we're not only going to be asked to do math, but remember, we always look at graphs. So if we graph force displacement, before we used to look at this kind of graph, a force versus displacement graph, force in newtons, displacement in meters, and we used to use the area of this graph to determine the work done. But when we talk about Hooke's law, the slope of this graph actually will tell us something new. And if I do my slope, so remember, slope is equal to the rise over run, the change in rise over the change in run. In this case, it would be the change in force over the change in displacement. And this should look like Hooke's law. Remember, Hooke's law says that force is equal to the spring constant times x. So what we're going to do is we're going to use our y equals mx plus b, just like we've used before. So if y equals mx plus b for a linear graph, and we've got force on the y-axis, and we've got slope, and we've got displacement on the x-axis, then our slope must be, by extension, sorry about that, guys. Our slope must be, by extension, the spring constant. So our slope is the spring constant on a force versus displacement graph. So that's what this is right here. So this is a new piece of information we can now get from force versus displacement graphs. For this one right here, it just happens to be 120, and if I look at my best fit line equation, up top, if you look closely, the slope in front of x is 120 newtons per meter, which would be the spring constant, or how stretchy my spring is. The final thing we are going to look at is what the area now tells us. So if we looked at our slope, it told us the spring constant. Our area still tells us the work or energy done. Now if I look at this graph that I gave you, the area under it to compress or stretch, elongate just means stretch, a spring is the area under the line, and the fancy name we give that is elastic potential energy. Now the elastic potential energy that we store in the spring, remember we call that U with a tiny s, because remember we use U for potential energy, and the way that we are going to calculate it is the way we used in our pre-lab packet, and that way is 1/2 kx squared, where k is the spring constant, x is our displacement, and U with the small s, U sub s, is our elastic potential energy. So remember, this would be equal to the work done by a spring. So we can find the work done by a spring using an equation or the area of a graph. We can find the force on a spring by using Hooke's law, F equals kx, or the slope of our line, which could give us the spring constant. And these are all the things that we need to know about springs.